Good afternoon, students. Welcome to the seventh lecture of Unit 1 of Refrigeration and Air Conditioning. So, in the last session, we have discussed about reverse Carnot cycle, the concept of reverse Carnot cycle, and the process 4 cycles of Carnot cycle, and also the problems related to the Carnot cycle. Today, in this class, we are discussing about the Bell-Coleman cycle and problems. So Bell-Coleman cycle or reverse Brayton cycle, Joule cycle. So their associated problems, right? Okay. So here, as already discussed, the Bell-Coleman cycle or reversed Brayton cycle or Joule cycle. So it is having three names: reversed Brayton cycle, Joule cycle, or Bell-Coleman cycle. So the Bell-Coleman was developed. The Bell-Coleman air cycle wise machine was developed by the Bell-Coleman and other scientist Lightfoot by reversing the Joule air cycle. So here also these are used for carrying the frozen meat, and also the figure shows the machine which has a compressor, a cooler, and an expander. See here. So it is an open cycle air Bell-Coleman and closed cycle or dense air Bell-Coleman refrigerator, right? So here, uh, if you see the both the cycles, so here we are adding some brine solution into the refrigerator for closed cycle. Here we are not adding any brine solution to this process, right? So see this figure and see the differences between the two figures. So what are the changes you can observe in the figure? What are the changes you can observe in the figure? So open air Bell-Coleman cycle and closed cycle Bell-Coleman cycle. So here you are having four processes, right? From refrigerator to compressor, from compressor to the cooler, from cooler to the expander, from expander to the refrigerator, right? So if you see the changes in the figure, from refrigerator to the compressor, you are having from the refrigerator to the compressor, you are having one thing. From compressor to the cooler, from again cooler to the evaporator, from evaporator to the refrigerator. So, but here you can see the same figure. You are having the four cycles, but only the thing is you are adding the brine solution into the refrigerator. You are removing the brine solution from expander to the refrigerator part, right? Now see the first cycle, isentropic compression process. So in this isentropic compression process, what you can observe here, so here the temperature, see the figure PV diagram, pressure, volume diagram, temperature, entropy diagram. Cold air from the refrigerator drawn into the compressor cycle, where it is compressed isentropically. So see the here pressure is increasing. So 1 to 2 means isentropically the pressure is increased. Isentropically the pressure is increased from 1 to 2. So when the pressure is increased, the volume is also increased, right? So here if you see the temperature from 1 to 2, the temperature is increased, the volume is decreased from V1 to V2. The volume is decreased from V1 to the V2. The volume is decreasing from V1 to the V2. Next, from 2 to 3, see here the 2 to 3, the volume is decreased from V2 to V3, but the pressure is constant. The pressure is constant. P2 is equals to P3. So if we see the temperature from T2 to T3. So the temperature is reduced from T2 to T3. Next, the temperature 3 to 4. See here the temperature 3 to 4 isentropic expansion process. So in this isentropic expansion process, the volume is increased, but the pressure is decreasing from P3 to P4. So if you see the changes in the temperature 3 to 4, the temperature from T3 is reduced to T4, right? Next, from 4 to 1. So if you see from 4 to 1, if you see from 4 to 1, see from 4 to 1, the pressure is constant, right? The pressure P1 is equal to P4, but the volume is increased from in this PV diagram. If you see the 3-4 diagram, 4 to 1, 4 to 1. So what happening in the 4 to 1? The temperature is increasing. T4 to 1, the temperature is increasing, and thereby the pressure is constant. So this is a cycle during the compression stroke. Both the pressure and temperatures are decreased, volume of air is increasing, and we know that during isentropic compression process, no heat is observed or rejected by the air. Next, if you see the constant pressure cooling process, so in the constant pressure cooling process, the warm air from the compressor, see the warm air from this compressor is passed into the cooler. So whenever the warm air is passing into the cooler, the cooling water is circulating into this chamber and making the warm water cool. The compressor is now passed into the cooler where it is cool at constant pressure P3, reducing the temperature from T2 to T3. So if you get a question here, then automatically you can first draw the figure, and you can explain on your own the temperature of cooling water T2 to T3. Next, as shown in the curve 2-3 and PV for the PV and TS diagram, the specific volume also reduces from V2 to V3. Volume from V2 to V3. So here the heat is rejected by the air during the constant pressure per kg. So at the second cycle, the heat is rejected కాబట్టి QR Q23 is equals to CP of T2 minus T3. Next, third one, isentropic expansion process. So what's happening in the isentropic expansion process? Here, the air from the cooler again is drawn to the expander. So the cool air from the cooler is going into the expander cylinder, and expanded isentropically from the pressure P3 to the refrigerator pressure P4, which is equal to the atmospheric pressure. The temperature of air during the expansion falls from T3 to T4. Then the expansion process shown by the curve 3 to 4 on PVS and TVTS diagram. Now the specific volume of air at the entry to the refrigerator increases V3 to V4. We know that during the expansion process what happens? No heat is absorbed or rejected by the air. So this happens at this process from cooler to expander. Again from expander it is going to the refrigerator. See here. So the constant pressure expansion process, the cold air from the expander is now passed toward refrigerator where it is expanded at constant pressure, and the temperature increases from T4 to T1. See the figure here. Again the temperature is expanding. The temperature is increasing from T4 to T1. This process by the curve and the PV and TS. So the heat from the refrigerator, the specific volume of air changes from V4 to V1. Therefore, the heat is absorbed by the air during the constant pressure expanding per kg of air. That implies QA is equals to Q of 4 minus 1, that is constant pressure T1 minus T4. So during the work done per cycle is equals to heat rejected minus heat absorbed. Heat rejected minus heat absorbed, that is equal to QR minus QA. So that implies Cp of T2 minus T1, T2 minus 3T heat rejected, T2 minus T3. That is cycle 2-3 heat is rejected. At cycle 2-4 cycle absorbed Cp of 1 minus T1 minus T4. Heat absorbed temperature 1 to temperature 4. Heat rejected temperature 2 to temperature 3. Therefore, the COP is equals to heat absorbed by work done. So this is a regular formula. Coefficient of performance heat absorbed by work done is equals to QA by QR minus QA. That is equals to CP of T1 minus T4 and QR, what is Q rejected? CP of T2 minus 33 minus QA. QA is this one. CP of T1 minus T4. Now, so CP cancel. So CP cancel on three sides. We are having T1 minus T4 divided by T2 minus T3 minus T1 minus T4. So upon doing the values, upon simplifying this process, we are getting 1. Therefore, the isentropic compression process at 1 to 2 is equals to T2 by T1 is equals to P2 by P1, this one. Next, similarly for isentropic expansion process 3 to 4, so the process is T3 by T4 is equals to P3 by P4, this one. Therefore, P2 is equal to P3 from the equations. So finally, we are getting. So upon doing the calculations, the isentropic compression expansion process, the equation can be written as COP is equals to T1 minus T4 divided by T2 minus T3 of minus T1 minus T4. So this is a formula for reverse Brighton cycle. So if you get any question in the exam point of view, just draw this figure. First draw this figure. So bell Coleman cycle, closed bell Coleman cycle. So just draw this figure. First one is refrigerator, compressor, cooler, expander. Later draw the PV diagram and TS diagram. So with this you can draw the diagram so that you can write whatever by saying the PV diagram as well as TS diagram. Right? Next. So based on this, we solve some problems, practice some problems. Now, in a refrigeration point, what happens in a refrigeration plant? The working on a bell Coleman cycle, air is compressed to 5 bar from 1 bar. So temperature changes T2 to T1, right? So temperature is, the air is compressed from decreasing from 5 bar to the 1 bar. Its initial temperature is 10 degrees centigrade. So what is the initial temperature? T1 10 degrees centigrade. The pressure 5 bar నుంచి 1 bar కి compress చేశారు. So isentropic compression, this one, right? After compression, the air is cooled up to 20 degrees centigrade. So what happens here? The air is cooled at 20 degrees centigrade in a cooler before expanding the pressure of 1 bar. Now determine the theoretical coefficient of performance of a determine the theoretical coefficient of performance of COP of a plant and a net refrigerating effect, taking CP is equals to 1.005 kg per kilojoules per kg. CV is equals to 0.718. So What is the given data from the question? The air is compressed from 5 bar to 1 bar unnadu. So P2 to P3 is equal to 5 bar. See here, pressure. So here P2, P3, P2 to P3. Here P1 to P4, P1 to P4. So what's happening here? P1 to P4 is 1 bar. This one P1, P4 is 1 bar. P2, P3 is 5 bar. Okay, P2, P3 is 5 bar. So the initial temperature is 10 degrees centigrade. T1 is equals to 10 degrees centigrade. That is Kelvin lo convert cheyandi 283 Kelvin. Next T3 is equals to 20 degrees centigrade. That is equals to 20 plus 273. That is 293 Kelvin. Right? Now taking Cp 1.005 kilojoules per kg. Cp is equals to, see here, coefficient of performance for net refrigerating effect. Taking Cp is equal to 100.1.005 and Cv is equals to 0.718. The PV and TS diagrams are shown in the figure. Now, so draw the figure as shown. Next. So if you see in the temperature entropy diagram, just see the temperature T1. T1 is equals to 283. T3 is equals to 20 degrees under 273 add చేయండి Kelvin వస్తుంది 293. So we have to find T4 and T2. Therefore T4 and T2 temperatures of air at the end of compression and expansion respectively. Right? Next. So from the isentropic process, compression and expansion process, gamma Cp by Cv, gamma of Cp by Cv is equals to, so in the question what it is given, this one 1.005 divided by 0.718, that is equal to gamma is equal to 1.4. Next. So from the figure, the isentropic compression process 1 to 2, T2 by T1 is equals to P2 by P1 gamma minus 1 by gamma. So substitute the values P2 5 by 1, 1.5 minus 1 by 1.4. So upon substituting, you are getting the value of T2 by T1 is equals to 1.584. Now for isotropic expansion process 3 to 4, T3 by T4 is equals to P3 by P4 gamma minus 1 by gamma, that is 5 by 1, 1.4 minus 1 by 1.4, that is equals to 5 to the ratio of 0.8. You are getting the value of 1.5. Next for isentropic expansion process, so we are having the T3 by T4 is equal to 1.5. Therefore T3 by T4 is 1.5, T2 by T1 is equal to 1.5. So the values we are getting same. Therefore T4 is equals to T3 by 1.584. That is, we know the value of T3. T3 is equal to 293 by 1.84. We are getting T4 value 185 Kelvin. Got it? So we got the temperature T4. Now the theoretical COP of the plant. Is equals to T4 by T3 minus T4. That is equal to 185 by 293 minus 185. That is equal to 1.713. Now, net refrigerating effect. We know that refrigerating effect is equals to Cp of T1 minus T4. Cp of T1 minus T4. Cp of T1 minus T4. That is equals to 1.005 by 283 minus 185. That is equals to 98.5 kilojoules per kg. So substituting the values there, we are getting the answer. So this is a way of concluding the problems for Coleman cycle or for is reverse column cycle. Now see the next one. The atmospheric air at a pressure 1 bar and temperature is -5 degrees centigrade is drawn in the cylinder. Is drawn in the cylinder of a compressor of a Bell Coleman refrigerating machine. It is compressed isotropically at a pressure of 5 bar. So compressed first you have to temperature 5 bar comes under which pressure? P2P3 or P1 P4. First you have to think that way. Compressed isotropically, expanded isotropically. So cycle 1, cycle 2 or cycle 3 or cycle 4. Immediately you get the picture into your mind and you can draw, then you can write the given data correctly. So in the cooler, compressed air is cooled at 15 degrees centigrade. So what it is saying in the question, from the cooler. Cooler means which temperature? Temperature 2 or temperature 3 or temperature 4. So cooler means from refrigerator to the that one, compressor to the cooler to the expander to the refrigerator. So the cooler at the temperature across the cooler temperature will be T3. So therefore, the temperature is cool at 15 degrees and above. So directly you have to keep in mind that is temperature T3. The pressure remains the same. So the pressure is same at T3. It is then expanded based on the 4-way graph. It is then expanded to a pressure of 1 bar. So P1, P4 is equal to 1 bar. That is for sure. Equal 5 bar and so the 5 bar is equals to P2 is equal to P3, that is equal to 5 bar. So if you see the PV diagram, so based on the PV diagram, so you can easily write the given data for the Bell Coleman cycle. Bell Coleman cycle. It is then expanded to a pressure of 1 bar expansion cylinder where it is passed to the cold chamber. So find the work done per kg of air and coefficient of performance of the plant. So for air pressure, the law of expansion PV to the power of PV to the power of 1 point is equals to constant. Law of compression is of PV to the power of 1 for constant. Specific heat of air at constant pressure is equals to 1 kg per kilojoules per kg Kelvin. So based upon the question, first write the given data. So here the pressure volume. See here 4 to 120 from expander to the refrigerator. 1 to 200 from refrigerator to the compressor. 2 to 3 means from compressor to the cooler. 3 to 4 means from cooler to the expander. So based on the concept, now based upon the question, write the given data. So what is the data? The atmospheric air at pressure 1 bar temperature is -5. So the atmospheric air at pressure is equal to 1 bar. So P1 is equal to 1 bar. So P1 is equal to 1 bar answer. Next, the temperature is -5 degrees drawn in the cylinder. So the temperature is 5 degrees. So -5 plus 273, 268. Next, if the compressor isotropically to the pressure of 5 bar, so that is 3. Compressor and pressure. Therefore, P3 is equals to 5 bar. P3 is equals to 5 bar. Therefore, in the cooler, the compressed air is cooled at 15 degrees. What is the temperature at T3? Temperature 2 T3 is 15 degrees. 15 plus 2 is 288 K. Remaining is the same. It is then expanded to the pressure of 1 bar. So expansion ఎక్కడ జరిగింది 4 లో జరిగింది. Therefore, P4 is equal to 1 bar. Right? Expanded at 1 bar in an expansion cylinder when it is passed to the cold chamber. So find the work kg and the COP of the plant. Right? So like this you have to data. So if you write the given data in the exam of this question for 8 marks or 7 marks, so if you write given data correctly, so you'll get score 2 marks. Next, so if you write what to find, so you'll get 2 marks. So if you write do some calculation part, so even though it is correct or wrong, if you do some calculation part, you'll get minimum 1 or 2 marks. So out of 8 marks, if your answer is wrong also, if your procedure is correct and formulas are correct, easily you can score 6 marks out of 8 marks. So that's why given data and minimum formula, minimum simplification is must. Even though you know the question or don't know the problems to solve, write something related to the question. Right now, so what it is given, n is equal to 1.2, gamma is equal to 1.4, cp is equal to 1 kilojoules per kg. So the figure is shown. So draw the figure first, later the work done per kg of air. So the work done across in the temperature T200, temperature T4. The temperatures at the end of the compression and expansion stroke, the work is done. The compression process 1 to 2 is isentropic and follows the law of P to the power of 4. PV into 1 to the power of 4 is equals to constant. Therefore, T2 by T1 is equals to T2 by P1 gamma minus 1 by gamma. So substitute the values. What is the P2 value? P2 value is 5 bar, P1 value is equal to 1 bar. Therefore, 5 by 1 by 1.4 minus 1 by 1.4, that is equal to 1.585. Therefore, T2 is equals to T1 into 1.585. T1 into 1.585. That is equal to 268 to 1.585. That is equal to 424.8. Now, so as you draw on the figure, you can easily identify pressure 1 to 2, pressure 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So the temperature is the same thing, 1 to 2, 2 to 3, 3 to 4, 4 to 1. Got it? Next. So the expansion process 3 to 4, this one, the expansion process 3 to 4 follows the law of P to the power of 1.2 is equal to C. Therefore, T3 by T4 by T4 is equals to P3 by P4. So T3 by T4 is equals to P3 by P4. That is n to the n minus 1 by n. Therefore, n is equal to 1.2 as we know. Therefore, P3 is equal to 5 by 1, 1.2 minus 1 by 1.2. That is equal to this value. So the answer is 1.31. Now, we know that the work done by the compressor during the isentropic process 1 to per kg of air, WC is equals to 1 to 2, that is gamma by 1 by gamma minus 1 into R T2 of T2 minus T1. Therefore, gamma 1.4 divided by 1.4 minus 1 into R into T2 value, T1 value. So that is 1. So how will you get the R value? Take the R value of A is 0.27287. So you get in the question, or you can achieve. Now, so you got work done is equal to 159 kilojoules per kg. Therefore, work done by the expander during the process 3 to 4 per kg of air, WE is to W3 to the 4, N by N to R T3 minus T4. Therefore, 1.2 by 1.2 minus 1 into R value minus T4. So the value is 118.3. The net work done per kg of air, the net work done per kg of air, W is equals to WC minus WP. 159 minus. So here WC 159 minus 118, that is equals to 40.7 kilojoules per kg. Work done per kg of air, W is equals to 40.7 by 40.7 kilojoules per kg. Got it? So this is the other way of solving the problems. So if you see second one, coefficient of performance of a plant. A coefficient of performance of a plant, heat absorbed during a constant pressure process 4 to 1. That is QA is equals to Cp of T1 minus T4. So Cp is equal to 1. We know that temperature 1 value 268 minus 220, that is 48 kilojoules per kg. Therefore, COP of the plant is equal to heat absorbed by heat work. Heat absorbed by work done. Therefore, QA by W is equals to 48 by 40.7, that is equal to 1.18. That is the total coefficient of performance of the plant. Right? So this problem you will get for 8 marks in the main exam. So in the mid exam, we will give this question, but for 2 or 3 marks. But the same question you can score 8 marks in the main exam. So coming to the next question. A refrigerator working on Bell-Coleman cycle operates between the pressure limits ఎంత ఇచ్చాడు 1.05 bar to 8.5 bar. సో దీనిలో ఎక్కువ ఏది ఉంది ఇది. సో దిస్ is P3 by P4 P1 and this one is P2 3. Air is drawn from the cold chamber at 10 degrees, compressed, and then it is cooled at 30 degrees before entering the expansion cylinder. So cooler ekkadundi, that is T3 is 30 degrees. The expansion and the compression follows the law of P to the power of 1.3 is equals to constant. Determine the theoretical COP of the system. So based upon the question, what is the given data? So 1 bar అన్నప్పుడు ప్రెషర్ లిమిట్స్ ఇచ్చాడు. ప్రెషర్ లిమిట్స్ 1.05 to 8.5 అన్నాడు. సో వాట్ ఇస్ ద ప్రెషర్ లిమిట్? P1 P4 ఒక లైన్ లో ఉంటుంది, P2 P3 ఒక లైన్ లో ఉంటుంది. సో బేస్డ్ ఆన్ దట్ P1, రైట్, P1 P4. సో కింద ఉంటుంది కదా P1 P4, P1 P4, P2 P3. So P1 is equal to P4 is equal to 1.05 bar and P2 P3 is equal to 8.5 bar. Now ఏమి ఇచ్చాడు క్వశ్చన్ లో? కోల్డ్ ఛాంబర్, ఎయిర్ ఇస్ డౌన్ ఫ్రమ్ ద కోల్డ్ ఛాంబర్, T1 ఇచ్చాడు. T1 is equal to 10 degrees. 10 degrees అంటే 10 plus 273, 283 Kelvin. Next T3. So T3 is equals to 30 degrees. 30 degrees అంటే ఎంత? 30 plus 273, 303 Kelvin. Then what is the question? N is equal to 1.3. The PV and TS diagram for the refrigerator working on the Bell-Coleman cycle is shown in the figure AB respectively. Therefore, let T2 and T4 temperature of air at the end of the compression and the expansion respectively. Since the compression and expansion follows the law of P to the power of PV to the power of 1.3 is equal to C, therefore write the formula T2 by T1 is equals to P2 by P1 to the power of n minus 1 by n. So what is the P2 value? 8.5, P1 value 1.05, 1.3 minus 1 by 1.3. So upon substituting we are getting the value 1.62, right? Therefore T2 is equals to T1 into 1.62. The value is 458.5 Kelvin. Similarly T2 by T1 తీసుకున్నాం కదా, T3 by T4 is equals to P3 by P4 n minus 1 by n. Again substituting the values 8.5 by 1.05 to the power of 1.3 minus 1 by 1.3, that is 1.62. Therefore T4 is equals to T3 by 1.62, that is equal to 303 by 1.62, that is 187 Kelvin. So we got the value T4, right? We got the value T4. So pressure 1 to 4 is equal to 1.05, pressure 2 to 3 is 8.5. So this is isentropic compression, this is expansion. So same thing, temperatures, write the temperatures. So itla meer raaskunnaru anukondi, once you will get the problem, first draw the PV diagram and TS diagram. So once if you draw the PV diagram and TS diagram for any question in R&AC or heat transfer subject, easily you can identify the given data. సో మనకి T4 T2 కనుక్కోవాలి, T1 ఇచ్చాడు, T3 క్వశ్చన్లో ఇచ్చాడు. సో T4 ఇందాక మనం కనుక్కున్నాం. T4 వాల్యూ, T4 is equals to this one. T2 వాల్యూ కనుక్కున్నాం, right? So T2 we got, T4 also we got it. Now the theoretical coefficient of performance. So this is a formula for theoretical coefficient of performance, right? COP is equals to T1 minus T4 divided by n of n minus 1 into gamma minus 1 by gamma T2 minus T3 minus T1 minus T4. So substitute the value T1 T4 283 minus 187 n by n minus 1 ఇది gamma minus 1, substitute the value T2 minus T1, substitute the values T1 minus T4, substitute the values. So taking this gamma is equal to 1.4. Therefore that implies COP is equals to 96 divided by, ఇవన్నీ substitute చేయండి. So this value is equals to 1.3 coefficient of performance of a plant. So like this we can solve the problem in the any sort of problems by simply drawing PV diagram versus TS diagram. Hope you understood the problems. So group lo ఉన్న వాళ్ళందరికీ I think you understood the problems, right? Shivaji 301, Dilip 304, 5. Okay. So what is the next problem? So you are having one more problem. So the time is less. Okay, we'll continue the next problem also. So the dense air refrigeration cycle operates between the pressures 4 bar and 16 bar అన్నాడు. So simply we can say 1 4 P1 P4 ఒకటైతే P2 P3 ఒకటి. So P2 P3 16, P1 P4 is 4 bar. The air temperature after heat rejection to the surroundings is 37 degrees centigrade, and air temperature at the exit of the refrigerator is 7 degrees centigrade. Okay, the air temperature after heat rejection, heat బయటికి వెళ్ళిన తర్వాత, the temperature is 37 degrees centigrade, and the air temperature at the exit of refrigerator అంటే T4. See here. So T4, T1 is equals to how much? T1 is equals to 280. So ikkada T1 is equals to, so the air temperature at the exit of refrigerator ఉన్నప్పుడు T1 వస్తుంది. The isentropic efficiencies of turbine and compressor are isentropic efficiencies 0.85 and 0.8 respectively. So N compressor, right, is 0.85 and 0.8 respectively. Determine the compressor and turbine work done per tonnage, COP, and power per tonnage, taking gamma is equal to 1.4, CP is equals to 1.005 kilojoules per kg Kelvin. So first draw the figure. So whatever the figure you know, first draw it. So like this, and write the given data. So what it is given, 4 and 16. Therefore pressure P1 to P4 is equal to 4 bar. Simply we can say pressure P2 to P3 is equal to 16 bar. Next time ఇచ్చాడు heat rejection to the surrounding outside. So our surrounding అంటే T3 వస్తుంది. T3 is equal to 37 degrees plus 273, that is equal to 310 degrees. So whatever the problem is given, first if the given data లో మీరు temperatures pressures proper గా రాయకపోతే you cannot get the answer.